We're back to the topic of capacitors now that we know a little bit about electric circuits, and now we're going to look at how capacitors function in electric circuits in general instead of just what the capacitor is and how it functions independently. So first off, we need to keep in mind when we're doing these analyses that really there are two moments in time that are important to think of. So typically with a capacitor circuit, something like this, we draw it with, instead of just a straight wire like this, we draw it with a switch. And then we can open or close the switch to start current flowing. So here we have some voltage on the battery, V0, and then here is our capacitor with a value of C. For the symbols, be careful on your capacitor symbol that you draw these about the same length, and that you make sure on your battery symbols that you have one line that's really short and one line that's much longer here. So when we close the switch, current starts to flow from the battery, and it flows from the positive terminal toward the negative terminal this way. So current flows that way. Initially, our battery starts out with positive charges over here and negative charges over here. And then these positive charges, because they have more area they can occupy, they're going to spread out. They push away from each other until our capacitor ends up with a bunch of positive charges on this end, and then these ones will spread out over here, and we get a bunch of negative charges on this end. Now, at some point, the concentration of positive charges over here and positive charges over here is going to balance out, and our charges stop moving in this direction and stop moving in this direction. So at that point, we no longer have any current flowing in this circuit. We have just our charges at rest. And then we might do something like, say, connect this to like a light bulb. And as soon as we make that connection, now we're going to have current flowing from our capacitor, and in this case also from our battery, but from our capacitor through our light bulb, so that our positives and negatives can move toward each other. So if we do this through a light bulb, we're going to get a large current passing through very rapidly, so that'd be a very bright light, and a very short-lasting light. So that'd be like the flash in a camera would be set up, something like that. Now, if we have more than one capacitor, we can find the equivalent capacitance, just like we found the equivalent resistance, except with capacitance, the rules are reversed. So if we have capacitors in parallel, to get the equivalent capacitance of that, we'll just add up all of the capacitors. So if we have, for example, a circuit that has, say, a battery, and then maybe a 10 microfarad capacitor here, and say a 20 microfarad capacitor here. The equivalent capacitance here would just be 10 plus 20 is 30 microfarads when those are in parallel. And we add those together because basically what we're doing is just making the plates on our capacitor larger. When we add another capacitor in parallel, this plate is connected to this plate by this wire, so we might as well just have the two plates connecting and or touching, and think of it as one larger plate capacitor. So we increase that area, the capacitance increases then. It increases to 30 microfarads. We'll go through a more detailed proof of that in just a minute. And then in series, so if we have a circuit like this, our overall capacitance, or our equivalent capacitance for series, looks the equation looks just like the equation for parallel resistors. And so we end up with 1 over C series is equal to the total of 1 over the CIs here. So if we had, say, 10, I'll just make them farads to, well, I guess units don't matter here, 10 and 20 microfarads, I have my 1 over the equivalent capacitance would be equal to 1 over 10 microfarads plus 1 over 20 microfarads. So 1 over the equivalent capacitance would be 1 over 10 is the same as 2 over 20, so 2 over 20 plus 1 over 20 would be 3 over 20 microfarads. And so my equivalent capacitance there would be equal to 20 over 3, which is 6 2/3, so 6.67 microfarads, which is less than either of these capacitors. Again, we'll talk about why that happens in just a minute. Our next learning target is back to those parallel capacitors, and this one will actually help us to understand another way of thinking of why we can just add the capacitor values together to find the equivalent capacitance. If we charge these up, so we have some current flowing to each of these capacitors then, and they're in parallel with each other, how that stored charge is going to be divided between those capacitors. Well, in general, for a capacitor, an important equation to know is that the charge on that capacitor, once it's been charged up, is equal to the capacitance times the potential difference from one point to another. So, in this situation, the potential difference from here to here is exactly the same as the potential difference from here to here. So here, that's equal to V naught, and here that's equal to V naught. So if I wanted to find the charge on C1, that'd be equal to the capacitance for C1 times V naught, and the charge on the second capacitor would be equal to the second capacitance times V naught. Or, since these V naughts are equal to each other, I could put those in an equation, set them equal to each other, and I would get that Q1 over Q2 is equal to C1 over C2. So if we had, say, values of 10 and 20 microfarads here, this one is double the capacitance, so it would hold double the charge. Now, if we take this back to the idea of the equivalent capacitance, so we want to make a circuit now that has just one capacitor in it instead of two. I'll make that a little more obvious. So that's a battery. There we go. And this has a value of C equivalent. We need that to have a total charge of Q1 plus Q2. Sort on that in order for it to really be an equivalent capacitor. So we say C equivalent has to be equal to the charge, the total charge, which is Q1 plus Q2. Oops. Divided by the voltage, which was V naught here. I'm just using Q equals CV, but rearranging here to find C. So I've got Q1 plus Q2 divided by the voltage, and so C equivalent, I can rewrite that as Q1 over V naught plus Q2 over V naught, which was, let's see if I do Q over V for the first one, that was just capacitance 1, plus Q over V for the second one was capacitance 2. So the equivalent capacitance, we just add the two capacitors together here. And again, on the setup here, if this is double the capacitance of this one, then this one stores double the charge of this one. Same voltage, double the capacitance, and this equation relates capacitance and voltage and charge. Okay, so now let's look at series arrangements of capacitors. These ones are a little bit more complex. So we have initially positive charges on the battery here and negative charges on the battery on this side. So we'll have current flowing in the direction that the positive charges move. At least that's the convention for stating this. And so we'll end up with a buildup of positives here, and we'll end up with a buildup of negatives here. Now this space in here is actually isolated. There's no connection to the rest of the circuit except for the field forces caused by the extra positives here and the extra negatives here. So these positives are going to pull some negative charges over this direction, and these negatives are going to call some positive charges over to this direction. But this is just a wire that's been polarized, basically. The net charge for this area, for the area between the two capacitors, is 0. There was no charge to begin with. Those charges have just been separated here. So, really, this is some positive Q here, and we end up with some negative Q here, and some positive value of Q here, and some negative value of Q here, but all the values there are equivalent. The charges will keep moving until they balance out in that way. Okay, so now let's say we want to find the voltage difference across these things. So we'll call this here delta V1, and that's going to be equal to Q over C1. Again, just using Q equals CV, just rearranged here. And here, delta V2 is equal to Q over C2. So that lets me figure out my potential difference there, but we need to also know that the amount of charge on each of these two capacitors is going to be equal. So I'm not writing Q2 and Q1 here, it's just Q. Now if I try and make a circuit that has just one capacitor that behaves the same way as those two capacitors in series, so I'll have the equivalent capacitance here. This will be V0 again. We know that V0 has to be equal to the voltage dropped across this capacitor plus the voltage dropped across this capacitor. So delta V1 plus delta V2. And then we had equations for each of those, so we can substitute those equations in. So V0 is equal to, forgot which way I had it. There we go, Q over C1 plus Q over C2. And the V0, that has to be equivalent to the same charge over the equivalent resistance. Okay, so then I can just divide everything by Q, and I find that my equivalent resistance is equal to 1 over C1 plus 1 over C2. Sorry, the inverse of my equivalent resistance is equal to 1 over C1 plus 1 over C2. And then the voltage across each of these we can calculate by finding this equivalent capacitance, finding out what that charge Q would be, and then calculating the voltage drops. So let's do an example with that. We'll say we have a 5-volt battery, and then 2 capacitors. We'll have 5.0 microfarads and 10.0 microfarads. And we want to know the voltage across each one of these, the change in voltage or the voltage drop across each one of those capacitors. So first off, we'll find the equivalent capacitance. So 1 over C equivalent is equal to 1 over 5 microfarads plus 1 over 10 microfarads. So we get our equivalent capacitance then is 3 1/3. 3.33 microfarads. So the amount of charge that's going to be stored on our equivalent capacitor or on each one of these original capacitors is going to be Q equals CV, so it's the 3.33 microfarads times the 5 volts So the amount of charge that's going to be stored here is 16.67, 16 and 2/3 microcoulombs. And so then delta V1 is going to be equal to Q over C1, which is the 16.67 microcoulombs divided by, we'll say C1 is the 5 here, so 5.0 microfarads. And we end up with 3.33 volts. And delta V2 is going to be the 16.67 microcoulombs again over 10 microfarads. So we get 1.667 volts. Okay, so our 5 microfarad capacitor, the smaller of the two capacitors, it's half the size of this capacitor, but it has twice the voltage drop of the larger capacitor here. So we could say in general that C1 over C2 is equal to V2 over V1. All right, and one last point here, the charge and the voltage on a steady state conditions for a capacitor connected to a circuit consisting of a battery and resistors. So you would think that that this would really change the situation a lot, introducing the resistor, because we know that we generally have some voltage drop across this resistor, but actually it doesn't change it as much as you might think here. So when we initially assemble this circuit or close the switch, connect to the terminals, we have current flowing in this direction. It goes through this resistor, so we have some voltage here and it drops by some amount here, and so we have some smaller value here. And so we would think, okay, well then this capacitor doesn't get as much voltage as it would have originally if this resistor weren't in place there. But what goes on in these situations is it still ends up, over the long term anyway, it still ends up getting to the same voltage across these terminals. So remember, what happens in these is current flows around here right up until there's no motivation for charges to move, until there's no more imbalance between the charges over here and the charges over here. So we're going to keep having current flow in this direction a little bit less rapidly because of the resistor there. We'll have current continue to flow this way right up until we have the same excess charge over here as we have here, and the same excess charge down here as we have down here. And that is true whether we have the resistor or not here. So that current will flow until there's a voltage difference here of V naught, or a potential difference of V naught there. So if we add resistance, all that does is make it take longer for this capacitor to charge up. And also we can make it take longer for the capacitor to discharge by adding resistance. But in the long term, we end up with exactly the same situation. Now, if you were to graph this, look at a graph of the voltage on the capacitor over time, what you'd find is you'd start out with a potential difference of 0, and then if we call this V naught, that's the voltage for the battery, we end up with a horizontal asymptote. So it looks something like this. So over time we get very, very close to V naught, so close that we would just say, yeah, we get to V naught eventually. And then as you add resistance, you change how gradual this curve is. So it becomes more and more gradual as you add more resistance, or it takes longer to charge. Your textbook gives an interesting example of this on page 757 with windshield wipers. So they have the intermittent settings that you can do on windshield wipers. Essentially what happens there is the little dial that you use to adjust how long it takes between wiper wipes is just changing the resistance on some circuit that includes a capacitor and what we call a variable resistor. And so when we make it have more resistance, then it takes longer for this capacitor to charge up, and we're waiting on the capacitor to charge to trigger the wipers to move. And so we increase the resistance across this thing, and that makes it take longer. So if there's just a really light rain, then you want a high value of resistance here, and so it takes a long time to charge up the capacitor. But if it's a little bit heavier, then you want a low value of resistance, and it takes less time to charge up the capacitor and less time between windshield wiper wipes. So that's capacitors. It's important to keep in mind that really they're just two plates that are storing charge, and pretty much all the consequences of that are what you'd be expected to know for an AP exam question. So keep in mind what a capacitor is, and that it's buildup of charges and two plates separated by an insulator, and you can pretty much derive the rest as you're working here.